Good morning, civil students. We will see Unit 3, Lighting Design. This is an electromagnetic spectrum starting from the higher wavelength radio waves towards the lower wavelength gamma rays. But the wavelength and frequencies are inversely proportional. C is equal to mu lambda. So the frequency increases from the radio waves towards the gamma rays. To remember the order of the electromagnetic spectrum, we have the mnemonics Roman men invented very unusual X-ray gun. R stands for radio waves, M microwave, I infrared rays, V visible, U ultraviolet, X X-ray and G gamma rays. Before going into the major contents of the topic, we will see few terminology. The first is the radiation and spectral quantities. Radiation quantities are set of quantities that measures the total amount of energy radiated, that is the energy either incident on the surface, absorbed by the surface, transmitted through the surface or emitted from the surface as a function of wavelength and frequency in the entire electromagnetic spectrum. The example is electromagnetic radiation, what we saw. The second is the spectral quantities, again a set of quantities that measures the total amount of energy radiated, but only in the optical and light region, that is the spectral region of the electromagnetic spectrum. Very good example is black body radiation and solar radiation. What is optical or light region? That is the electromagnetic spectrum, which is composed only of ultraviolet, visible and infrared radiation. This is the spectral plot of black body radiation, a graph drawn between radiation intensities and wavelength. It is composed only of optical or light region having ultraviolet, visible and infrared electromagnetic radiation. Based on the recorded spectrum, the radiation studies can be either radiometry or photometry. Radiometry is a study that deals with the detection and measurement of electromagnetic radiation across the optical spectrum. Example, black body radiation and solar radiation. Whereas photometry is the subset of radiometry that deals with the detection and measurement of spectral radiation which are sensitive or visible to the human eye. Example, colors of rainbow. The parameters which are used to measure the radiometric quantity are called radiant quantities. And the parameters which are used to measure the photometric quantity are called luminescence quantities. In general, luminescence means brightness. The radiometric quantities are applicable only for optical spectrum or light spectrum, whereas the photometric quantity are applicable for visible spectrum. In physics, the energy is denoted by the letter capital Q, power by the flux phi, intensity by capital I, radiance capital L and irradiance capital E. If small letter e is written as subscript, then these quantities are referred to radiant quantities. Similarly, if small letter v is written as a subscript, then they denote the luminescence quantities. This tabular column shows the list of radiometric and photometric quantity, their symbol and units. Let's summarize both the radiant and luminescence quantities. The radiant quantity should start with the word radiant, whereas the luminescence quantity should start with the word luminous. Radiant quantity have the subscript E which denotes energy. The luminescence quantity have the subscript V which denotes visual, which we can see. The definitions which are defined for the radiant quantity is very similar to the luminescence quantity. As both are one-to-one related, the photometric unit can be written in terms of radiometric unit as photometric unit equal to k of lambda into radiometric unit, where k of lambda is the proportionality constant as a function of wavelength and its value is 685 V of lambda, which represents the peak eye sensitive value recorded at the wavelength 555 nanometer. Now we will define each radiant quantity. The first is the radiant energy, the total amount of energy carried by the electromagnetic spectrum. The second is the radiant power or radiant flux denoted by phi suffix E, is the total amount of radiant energy transmitted per unit time. Usually the power is the rate of change in energy. The third is the radiant intensity. It tells you the total radiant energy radiated from a point source per solid angle per unit time. So you have a point source from which the radiant energies are radiated, forming a solid angle d phi with the angle of inclination d omega. Therefore, IE is equal to d phi E by d omega. The next is the radiance, is the total radiant energy radiated from a point unit projected area per unit solid angle per unit time. So here instead of a point source, we have a projected area capital A from where the energy is radiated, forming a solid cone with a d phi, and the angle of inclinations is theta and d omega. Therefore, LE is equal to d2 phi by d omega dA cos theta. And the last is the irradiance, is the total amount of radiant energy incident upon a unit area per unit time. So far, we have the radiant energy emitted from the point source or area. Here you have the radiant energy is going to be incident on a particular surface. To understand easily, let us consider a laser source. So you have a laser source. When it is focused onto the wall or a screen, you can see the projections of the laser source forming a solid angle d phi. When the same laser source is passed through a liquid medium and then is focused on the screen or the wall, the liquid medium acts as the projected area. The laser source which comes and falls on the liquid medium will act as the irradiance. The same definitions are applicable for luminescence quantities where radiant energy is replaced by light energy. Now, let us consider a light beam incident on a one-dimensional plane or a straight line or x-axis. The beam incidents in the x direction and gets reflected along the same x direction. We say the beam is reflected in plane or specular. Consider a two-dimensional plane where the beam incident in the x-axis and gets reflected in the y-axis, and they are out of plane. In such situation, if a human eye or detector is placed above, a total area of 180 degree starting from 0 to 2 pi is visualized, which forms a hemispherical view, and this is called directional hemispherical. A hemispherical view is one observed in planetarium. Another example is recording X-ray for a unknown sample material. If the hemispherical view is due to the reflections of radiant flux, then it is called hemispherical reflectance, denoted by rho lambda. Otherwise, if the hemispherical view is due to the transmission of radiant flux, then it is called hemispherical transmittance, and it's denoted by tau lambda. Before concluding this video, let us state Lambert cosine's law and inverse square law. The Lambert cosine's law states that the intensity of the light illuminated is directly proportional to the cosine angle formed between the incident beam and surface normal. The illumination is maximum at theta is equal to 0 degree because cos 0 is 1. The inverse square law states that the intensity of light incident on a surface is inversely proportional to the square of the distance between the source and the surface. So as the distance between the source and surface increases, the intensity of light falling on the surface decreases. Thank you.